Okay. All right. Because I really do want to call somebody, but I may have to wait till Monday. All right. So we're doing. This is chapter 8. Best approximation in the infinity norm, also known as the maximum norm. So here's the problem that we're to attempt to solve. And I say attempt because we're not going to really get that far with it. Okay, so if we're given some function f that is in this vector space, and I defined this last time, this is a continuous functions on the interval AB. So this is very standard notation that you need to know. So given such a function, we want to find a polynomial P such that the infinity norm of the error f minus p, which is defined to be the maximum for x in AB of the absolute value of this difference, is as small as possible. Okay. Now, one thing that we do know is we have the a theorem. Actually, I want to make sure I get the name of this theorem right. So, I'm not playing on my phone, I swear. This time. Okay, I know that Weierstrass's name is in it, but okay. Oh, it's not. Okay, it's not that one. Okay. Okay. That bugs me because I'm not really finding it here. Okay, that's going to drive me nuts. So there's a theorem about if you choose, I'll write it down momentarily, error tolerance like epsilon. Okay, I think I have it. It was just called by a strange name. Okay, so it's not Bolzano-Weierstrass, it's a completely different theorem. The Weierstrass approximation theorem, which is also known, I guess, sometimes a number of names attached to it, like a Stone-Weierstrass approximation theorem, but I guess Stone is not worth remembering much of the time, whoever he is, or was. It says that for any epsilon, there exists a polynomial P such that this error, the infinity norm, is less than epsilon. So you can pick epsilon to be as small as you want. You can always find a polynomial so that f is uniformly approximated on AB. So we're assuming a particular interval AB in this case. Now here's the problem though. The smaller you choose epsilon, your polynomial P might have to be a very large degree. So don't expect that you can find some simple polynomial like a quadratic or cubic function that's going to approximate a given function f that well. But yeah, if you don't care how high the degree gets, yeah, you can get as close as you want. Good luck with that. Okay. Now, that is not the problem we're going to look at here. Instead, okay. So given a fixed degree, n, we want to find a polynomial that I'll call p sub n, such that the infinity norm of this difference is minimized and we want to find a polynomial of degree n that makes this error as small as possible. So we're minimizing this error over all polynomials of degree at most n. All right. Now, okay. So Pn, if we could find the one that achieves its minimum, is called the Minimax polynomial. Of degree n. Okay, so for any fixed n, there's a different minimax polynomial generally. Okay.
Excuse me, by that you mean mean or max?
What?
It could be mean or max?
No. Okay.
Is the name?
The reason why we call it minimax is the infinity norm is also known as the maximum norm. So we're trying to find a polynomial that minimizes the maximum norm.
Okay.
Yeah. Okay. Now, one thing I can tell you is unfortunately, this is why I don't like this chapter actually, because I will not be able to give you an algorithm where you can feed it an arbitrary function f that's continuous in AB and specify degree n, and here's an algorithm that churns out the minimax polynomial of that degree. I can't do that. That problem is not solved. And this totally flies in the face of what numerical analysis is about. Numerical analysis is about finding algorithms to solve certain problems, actually give you us a approximate solution. We could try to get close to minimax. We'll be able to do that, but only in certain isolated cases can I say, here's how you get the minimax polynomial. And that just rubs me the wrong way. And that's why in the next chapter we will settle for an approximation in the 2 norm for which you can actually compute the polynomial in any case. And that is generally not as good an approximation as the minimax polynomial, but if you can get close, then that's a good thing. Okay, so it's really more from a theoretical interest, this minimax. Okay. Now, okay. So first I want to say a few things about existence and uniqueness. Okay, so first about existence. You can think of Pn as a polynomial of degree n, therefore it has n plus 1 coefficients. So you can think of this as as a function of the n plus 1 coefficients. So, and I'll call those coefficients A0, A1, A2, up to AN. So you can think of a defined error function E as a function of these coefficients, A0 up to AN, to be the infinity norm of your f, whatever f is, minus this polynomial. Okay. So the idea is you want to try to minimize that function on the interval AB. Now the thing is, okay. Here you have n plus 1 variables. So you can think, okay, the domain of this function is Rn plus 1. But the thing is, this function is continuous. So as you vary A1, A2, A0 up to AN, this infinity norm will vary continuously, so that's fine. Also, okay. There exists a compact non-empty subset of Rn plus 1 such that the norm is less than or equal to the norm of f itself plus 1. Like for instance, certainly if you said Pn equals 0, then this would be satisfied. So the idea is you're not considering coefficients within all of Rn plus 1. You can limit yourself to a certain subset because there are certainly polynomials that satisfy this. Also, because it's less than or equal to, this set of polynomials that satisfies this is a closed set. And when it's a bounded set because the coefficients can only get so big before this is violated. So if you've taken real analysis, you know that or you should know, that a compact set is both closed and bounded. And one thing we know about a continuous function defined on a compact set is that this function has a minimum. Okay. It's like you learn in Calculus 1. A continuous function on a closed interval has a minimum and a maximum. More generally, a continuous function on a compact set has a minimum and a maximum. We don't care about the maximum in this case. It's a minimum that we want. But I'm saying also to tell you the minimax polynomial exists. So for whatever f that's a continuous function, whatever degree you pick, n, there is a minimax polynomial. Okay. And I can tell you it is unique. I'll have more to say about that later. I guess I can state some theorems about the minimax polynomial. Now, whether we can find this minimax polynomial that we know exists and is unique, that's another matter entirely. Okay.
Is that a real word?
What?
Minimax?
No, it's made up for this.
Okay, that's fine.
Yeah. It's not a regular English word. Okay. So what I'm going to do is, I have a couple examples. Okay, but first, I have a theorem I want to state about the Minimax polynomial, what we know about it in general. Okay. Okay, so one thing that characterizes the Minimax polynomial is a very important theorem called the oscillation theorem. Okay. So the oscillation theorem says that if you have some polynomial little pn, which is in big Pn, this is the space, or like a vector space of all polynomials of degree at most n. If it is the minimax, and I'm getting tired of writing polynomial out in full, so I'm just writing poly, as you can see, deal with it, of degree n, for a given function f that's continuous on AB, then there exist n plus 2 points within AB. And it could be n points, but they're distinct. So x0, x1, x2, etc., all the way to xn plus 1 that fall within the closed interval AB. And these are given a most unfortunate name. They're called critical points. Not the same as critical points that you learn in calculus, although the name is not entirely inappropriate for a reason I'll put on it a little bit. Okay, critical points of f on AB. Now, what is it about these? What do we know about these points? So it turns out at these points, if I look at the error at those points, it is actually equal to the infinity norm. In other words, it's where the error hits its maximum. And that's quite weird that, because you see, because the infinity norm is supposed to be the maximum deviation. And you might think, okay, you're looking at the error f minus Pn, that this maximum is achieved at a point, and you might think, oh, maybe it's only achieved only at that one point. But no, it hits it exactly n plus 2 times. And there's more. You can say that the error at each of these points is opposite in sign. These p's should be pn's. So the sign of the error keeps going back and forth between positive and negative. That's why it's called the oscillation theorem. So what this means is, okay, and this statement is true for I equals 0, 1, 2, up to n plus 1. So in other words, if you were to examine the error, f minus Pn, on the whole of the interval, then it would be a very oscillatory function. Now, how much oscillation there is depends on the degree n, because you have n plus 2 points. And the reason why it's not entirely inappropriate to call them critical points, because what does a critical point normally mean? How do we normally use that term in calculus? Yes, where minimax occurs. So at these critical points is where the maximum error is occurring. Or actually, because of oscillation sign, minimum and maximum if you drop the absolute value. So really they're not critical points of f, but this is what the textbook calls them. They're really critical points of the error. If f was differentiable, which it is not necessarily. Okay. And it is this result that I won't go into the details here, but it can be used to prove uniqueness. That if there were the idea is if there were two polynomials where you look at the error between them and f, and you have n plus 2 critical points for both. That you use that to prove that the polynomials must be equal. Okay. So this result can also be used in certain cases to come up with the minimax polynomial. So now I can show some examples. Actually, yeah, I have 3 examples where it actually is possible. It's just that they're not very general. All right, so the first example where we can find a minimax polynomial is since we have f defined continuous on a closed interval, f has a minimum within the interval at x equals squiggly, and it has a max in the interval at x equals eta. So in this case, it's very easy to find a minimax polynomial of degree 0, which is just a constant function. So a minimax polynomial of degree 0 is equal to just the average of the maximum value, minimum value of f and the maximum value. Now, can anyone explain, using the oscillation theorem, why P0 has to be the minimax polynomial of degree 0? Can you explain why it actually does satisfy these conditions here for the n equals 0 case?
Is that going to be the only P0 in this case?
Oh,
It's only one critical point.
well, how many critical points should there be?
0?
N plus 1.
Degree 0?
Well, yeah, n plus 1, and if n is 0, then just 1.
N plus
No,
2.
n plus 2. n plus 2 critical points.
Oh, is that okay?
Yeah, so 2 critical points. So, okay, I'll draw an example function. Okay, so I'll put a max and a min. So here is eta, and here is xc. So we look at these values, we're going to go between any, okay, that's not the minimum. That's the minimum.
We have a good imagination.
What?
I said we have a good imagination.
Okay. You're going to need it. Okay, so what happens here at this point, at eta, the error, f minus p0, is going to be the maximum minus 1/2 f of xc plus f of eta. And if you work all that out, that's going to be f of eta minus f of squiggly. Now, squigglies are particularly bad because it's been a long day. All over 2. That's what's happening at eta. What's going to happen at squiggly? Based on the picture or from the algebra? What?
I said they both look like squiggles.
Oh, that's true. But
Yeah, I know it's beta.
Okay.
Sorry, I didn't mean to say it out loud.
Abby, you
It's going to be f of squiggly, and then I guess I'm not 100% positive if you're gonna still subtract the, here, well, yeah, you can always subtract here.
Yeah?
Yeah, so then. The equations are gonna be similar, it's just you're gonna have.
Is there gonna be a positive?
No.
squiggly at this point?
Well, okay, f of squiggly will have a plus sign.
And
Yeah,
the
and
eta
then
will
the
have a
eta will-
negative sign.
Yes,
So like the letters.
yeah, look at the picture. Same distance,
Yeah.
but opposite sign. Yeah, because so at squiggly, you have f minus p0 again. And but f is now going to be f of squiggly minus the same thing. And now, yeah, f of, so this is going to be the negative. So we have, for degree 0, just a little bit of oscillation, because we have just those two critical points. So it's almost like you want to find a polynomial of a certain degree that's going to weave its way through the graph of f in such a way that you have these gaps of same size, as large as possible, but alternating sign. That's how you get a polynomial as close as you can to f. It's just that it's particularly easy to do in a constant case, but if you go to higher degree, then you have a much harder time. Okay, so any questions about this one before I go to 1 degree higher? All right. Now, so now let's look at n equals 1. Now, I can't tell you how to get the minimax for a general function, a general f that's continuous in AB. But if we make some assumptions about f, then it's doable. Okay. So we have our f, but we're also going to assume that it's in C1 of AB. And what I mean by C1 is continuously differentiable. And we're also going to assume that f prime is monotonic. So f prime is always increasing or always decreasing. Now, we're not assuming second derivative, but if there is a second derivative, that would mean that f double prime is either always positive or always negative. In other words, you have the same concavity throughout AB. So it's going to be a case, something like this. Okay. Now, because you're looking for a minimax polynomial of degree 1, we're going to find P1. How many critical points should there be?
3.
Yeah, we're going to be 3. Now, okay. So our polynomial P1 is going to have this form. Constant plus another constant times x. So if you look at f prime minus P1 prime, now P1 prime is just going to be C1. So, and the thing is and f prime itself doesn't change sign. Okay, so on AB. Okay. So if we were to try to find the maximum or minimum of the error, so critical points, okay, so we would take the derivative of the error and set it equal to 0. But the thing is, f prime itself doesn't change sign at all on AB. Like here, it's always increasing. Now, if we subtract C1 from it, then yeah, it could go positive and negative, but how many sign changes can you possibly have?
Two. Because there's 3 critical.
Well, forget about Minimax. I'm just talking about the derivative.
The derivative's gonna be a degree too, so.
Well,
Well, no.
f itself is not a polynomial.
Oh.
But we do know that its derivative doesn't change sign. So I guess, let's suppose the derivative is always positive. Now you subtract C1 from it, so you're taking a curve that doesn't change sign at all, and then you shift it down a bit. So how many times could it possibly change sign?
What?
Once.
Is
One.
it moved?
Yeah. In other words, if you're looking for critical, they call it, let's call them Cal 1, critical numbers, within AB, you're only going to get 1 at most. So if we're trying to find the maximum or minimum of the error, we cannot get them from critical points in here alone. So where else do you find maximum and minimum, like in Cal 1? Yeah, if you look at critical points, and where else do you look? The endpoints, A and B. So this is why the assumption of f prime being monotonic is important. Because if it's always increasing or always decreasing, what that means is A and B have to be critical points. Now we're back in terms of the oscillation theorem. So you have 3 critical points because of the oscillation theorem. 2 of them must be at the endpoints A and B, and then you'll have one other somewhere in between. Okay. So this helps a great deal. And there exists another critical point that I'll call D, and it has to be in the interior.
Excuse me.
Yeah.
I don't understand how that minus C1 guarantees another change in sign.
Well, depending on the value of C1, there still might not be. But the point is there's at most 1. And because basically you're taking a curve, actually a curve much like this actually, that's always increasing or always decreasing, and you're shifting it. And if you happen to shift it across the x-axis by subtracting C1, you'll get a sign change. Otherwise you won't.
And C1 could be anything?
Right now C1 can be anything, yeah. Now, if we're going to, the thing is we need a critical point, we need a sign change. So we need to make sure to choose C1 so that we'll actually get one. But the point I'm making is, whatever f prime is, and you subtract C1 from it, you are never going to get more than 1 sign change. And that's why we need A and B to be critical points.
I mean, by that I mean if it was plus C1, then we could say the same thing, right?
Yes, yeah. Plus, minus, doesn't matter, because right now C1 is allowed to be anything. But yeah, now we will need to make sure that C1 is of a good value to get a sign change, but there's at most 1 sign change.
What is that letter in front of the very last name in NAB? D?
D.
Oh, okay.
Yeah, so that's what we're naming the other critical point.
Oh, I thought so. It was just the first D, so.
Yeah. So now that we know something about critical points and how the error is supposed to behave, we can try to figure out something about this polynomial. So from the oscillation theorem, we have a following, that the error at x equals a, which is f of a, minus c naught plus c1 times a, so we're just plugging in x equals a, that is equal to some maximum error that I'll call capital A. Now I don't know if it's positive or negative. Now, at the interior critical point, D, I look at the error again. So if this is the error at the first critical point, what should the error be at the second critical point? By the oscillation theorem.
minus a.
Minus A. And then I go to B, the last critical point. Yeah, so what should I have here?
A.
Yeah. So it keeps alternating sign. Okay. So now what we can do is do some elimination. For example, I can subtract the first and third equations, and that'll cause the C naughts to cancel out and the A's to cancel out. And what works out really nicely is, so from these two equations, subtracting them, I can get that a value for C1. It's f of b minus f of a over b minus a. Can anyone tell me what that represents? That difference quotient. It comes up all the time in Cal 1.
It's the average rate change.
Average rate change on the interval AB. It is also the slope of the what? Secant line, using the points A and B. Okay. So what that means is it has the same slope. So in other words, the minimax polynomial is parallel to the secant line. We just need to figure out what C naught is supposed to be. Fortunately, we can get that too, because I can use, now that I know what C1 is, I can use the first two equations, like I can, okay. Yeah, I can add them, because if I add these two equations, the right sides will cancel. So C naught turns out to be 1/2 f of a plus f of d minus C1, which I know, times a plus d. So I can almost solve this completely. There's only one thing in here that I don't actually know. Of all the quantities that I have here, what's the one that I don't actually have a value for?
G?
Yeah, or d itself. Yeah, because d is the unknown point. That's the next critical number. Okay. Now, so the thing is, okay. Okay, so I need some value for D. So it turns out that by the, okay. That's what I get for not putting enough stuff in my notes, because the statement that I have in here, I can simply tell you what it is, but I'd like to be able to explain exactly why. Okay. Because if I draw the graph again, because we know that this is the secant line between A and B. Now that's not the minimax. All we know is that the minimax is parallel to it. So I really want to shift it down to a certain extent so that the gap between this line so here we have a gap which it's hard to see because it's very small. That's A. Here's the gap here is also A. And then this gap right here at wherever D is, that gap is minus A. So, okay, this is going to drive me nuts. So as far as where that error is actually going to occur, because this is equal to the derivative at some point, which I'll call, I need to call it something else, but well, I'll call squiggly. Now, what theorem from calculus gives us this? The average rate of change equals the derivative or instantaneous rate of change at some unknown point.
Is that not the mean value theorem?
Mean value theorem.
Okay.
Yeah, there is an intermediate value theorem, but yeah. Yeah.
That's very similar.
I know, it totally seems like splitting hairs.
C, right?
Yeah, it's normally written as F prime C, but
I mean, that's fine too.
yeah. Okay. Okay. Now, what I have written in my notes is it actually turns out to be F prime of D. There's a point at which the slope of a tangent line is equal to this C1. Okay, so I can tell you why. If I take this equation right here, and I think of D as being a variable, what do I get if I differentiate this equation with respect to D?
F prime of D minus C1
Equals
0.
yeah. So there you go. Okay. Well, I saved my ass. No, that would have like totally killed me if I couldn't figure that out, and I wish I'd put that in my notes. Okay. So that's why it's equal to that point. So, so if we're able to find the unknown point where this equality happens, and depending on, yeah.
I'm sorry.
Okay. Well,
Yeah.
I'm glad that reached you.
Yeah.
Okay. Then, and depending on the function f, maybe we can do that. Then you can construct a minimax polynomial for that case. Okay. Also, this point, this is unique due to the fact that f prime is monotonic. Because it's only, if f prime is only going to hit the value C1 one time, because it keeps increasing or decreasing. Okay, so that's the minimax polynomial of degree 1 if you have this constant concavity. Otherwise, good luck finding it. Okay. Now, there is, here's another case. Oh, yep, I'm still not calling anybody today. As I fall even further behind. This is hopeless. Well, okay, my next two victims, you better be ready to present efficiently. Otherwise, I won't feel like calling anybody on Monday either. Okay. Good practice for Math 500. Okay. All right, so my next example can show you the Minimax. Suppose my function is x to the n plus 1. And I want to find the Minimax polynomial of degree n. Okay. And it turns out I can just write down what it is. P of x turns out to be x to the n plus 1 minus 2 to the minus n t n plus 1 of x, where this t n plus 1 is a Chebyshev polynomial of degree n plus 1. Now, the reason for the 2 to the minus n is that we talked about Chebyshev polynomials before, and what I mentioned was that the Chebyshev polynomial leading coefficient keeps doubling because you have this relationship Tn plus 1 is equal to 2x Tn of x minus Tn minus 1 of x. So that the doubling keeps occurring. So, and also we have the initial conditions. T0 is 1 and T1 is x. So Tn has a leading coefficient of 2 to the n minus 1. So I use this to cancel out that leading coefficient. So this whole thing is a monic polynomial, leading coefficient of 1. And also, it's degree n plus 1. So what that means is, even though I have x to the n plus 1 here, and this is of degree n plus 1 also, what's going to happen to those x to the n plus 1 terms in this whole thing? They're going to cancel. Yeah, because I have a leading coefficient of a minus and a leading coefficient of 1. So the x to the n plus 1 terms cancel, so the whole thing is guaranteed to have degree n. Now, why is this a minimax? Well, the error is x to the n plus 1 minus Pn. So I plug this in here, and I have the x to the n plus 1s that are going to cancel. So the error is 2 to the minus n Tn plus 1 of x. So what I want to know is, where do Chebyshev polynomials have their maxes and mins? And the nice thing is there's a formula for that. So in general, Tn has its extrema at these points. Xj tilde, which is cosine of j pi over n. And because it's a cosine, I'm sorry, I forgot to specify the interval. Minus 1 to 1. You kind of need that. Okay, you need an interval and an f and a degree. Okay. So because these are cosines of various points, these fall within minus 1 to 1. Oh, and j runs from 0, 1, 2, up to n. Okay. So what's interesting is Chebyshev polynomial degree n, it has n roots. But these are not the roots. These are the extrema. They're n plus 1 extrema. So also, this follows degree n plus 1. So this has n plus 2 extrema. Those are the critical points for the oscillation theorem. And to see why, we need to plug in those extrema. So, because what are the extreme values? Now this is for Tn, but it works the same way. So Tn of xj tilde is equal to, well, here's the formula. Tn of x is cosine of n inverse cosine of x. So if I use this formula, I'm going to get cosine of n inverse cosine of xj tilde. But xj tilde is itself a cosine, which cancels with the inverse cosine. And then this n is going to cancel with this n. There's cancellation everywhere. It's a cancellation bloodbath. Which is great for us, because then we get cosine of j pi. What is cosine of a multiple of pi?
0,
No.
1.
Sine is, okay, is 1 half the time. Yeah, plus and minus 1. Specifically, it is minus 1 to the j, which is exactly what we need. Alternates between plus and minus 1. So the error is equal to plus or minus 2 to the minus n. And we have n plus 2 points at which the error is reached, the maximum error, and it keeps alternating signs, so it satisfies all the conditions of the oscillation theorem. Because it really is, actually is an if and only if kind of deal, due to the uniqueness. Okay. My spacing was off. And I notice that as the degree increases, the error gets smaller because this is 2 to the minus m. Okay.
So it goes plus or minus 2 to the negative 1?
Yes. Yeah, it keeps alternating back and forth between those two values.
Oh, because it's.
Oscillation theorem. Okay. So at least in that case, so these few cases, we can compute the Minimax polynomial, but unfortunately, generally, we cannot. Okay. All right. Now, one last point to make about Minimax. So actually, okay, so at least after today, I will not be any further behind. I can start the next chapter, because this is a quick chapter, which is a good thing, because I don't like it. I love the next chapter, though, because that's orthogonal polynomials, which are the most beautiful mathematical creations ever. So, well, hey, they give me so much of my research program. So, okay. So I want to say a word about, because what we're doing here, of course, is not interpolation. We are not expecting f to agree with Pn at any particular points. It will agree at certain points because it keeps oscillating around it. But there is a connection between interpolation versus approximation, which is what we're doing now and in the next chapter. Okay. And I've mentioned this before, Chebyshev polynomials, but it's worth reviewing. So let's suppose f is n plus 1 times continuously differentiable, a word I never like to write out in full, on AB. And if I let Pn be not the minimax, but the interpolant. So we're back to polynomial interpolation, like a Lagrange form. And we use the Chebyshev points. For the interval AB. So what that means is, so these are Chebyshev points, where I take 1/2 b minus a times xj plus 1/2 a plus b. where xj are the roots of the Chebyshev polynomial of minus 1 to 1. All right, this is for j going from 0 to n. So these are the roots of Tn plus 1. But what we're doing with those roots, these roots are in minus 1 to 1. And squiggly j here takes these values from minus 1 to 1 and maps them to AB. So we're just doing shifting and scaling to put them in AB. Okay. Now, what is the error in this approximation? Because we're using a formula that you guys, if you've been doing any of the chapter 6 problems, you've been dealing with the Lagrange interpolation error. And that's what we're using here. Okay, I think I can do this in 5 minutes. Okay. So the error, so that's f minus pn. So the normal error formula is n plus first derivative, which is why we need to make an assumption about the derivatives, over n plus 1 factorial times x minus x naught, x minus x1. Well, actually not x, squiggly, because those are our interpolation points. Okay. Now, this right here is a factorization of the Chebyshev polynomial, almost. It's the Chebyshev polynomial degree n plus 1 because the squigglies are the roots. The only thing we have to correct for is a coefficient because this whole thing has a leading coefficient of 1. It is monic. So I need to include this factor of 2 to the minus n there. And the other thing I need, well actually, it's not a factorization of Chebyshev polynomial, it's except, well it almost is, except it has to be mapped from minus 1 to 1 up to AB. So I need to include an additional factor of b minus a over 2 to the n plus 1. Okay. Because we have to take into account the shifting and scaling that, really not the shifting, just the scaling that happened to go from minus 1 to 1 to AB. So I can simplify this to n plus first derivative at some unknown point over n plus 1 factorial, 2 to the n, and then we have b minus a over 2 to the n plus 1 times tn plus 1. Okay. Oh, actually, sorry, not x. But t of x. Because once again, I have to, tn plus 1 is defined as minus 1 to 1. So t of x is 2x minus a minus b over b minus a. So this maps the interval AB into minus 1 to 1. So we have to keep mapping back and forth between these intervals, unfortunately. Okay. And the reason why I need to explain this, so one of these linear factors, x minus squiggly j, oh wait. Because I can write this as t of x minus xj, as long as I multiply by b minus a over 2. So if you take into account how these two relate to one each other, because I have a formula for it over there, and how these relate to each other, then you can see why this works out. So if you really, really want to, you can convince yourself of that. But it has to do with the mapping from -1 to 1, an interval of width 2, to AB, an interval of width B minus A. Okay. Now, so here's our error. Can anyone tell me, knowing that this is a Chebyshev polynomial of degree n plus 1, how many times does this change sign within AB? No. Warmer.
It's not n plus 1?
It is n plus 1. Because what's a sign change? It's a root. Yeah. Well, unless if you double root, but Chebyshev polynomials don't have double roots. Because they have these distinct linear factors. But yeah. So n plus 1 roots gives us n plus 1 sign changes. So the error is changing sign n plus 1 times. But how many sign changes do we want from a minimax? N plus 2. So we fall short. So that's why this Chebyshev interpolant is not the minimax necessarily. Unless there happened to be another sign change, maybe do this. That'd be cool. But we don't know if that happens. So what that means is we can say that the Chebyshev interpolant is what we call near minimax. So it has almost the correct number of critical points. And actually these sign changes occur at interior points, so within the interior of AB, because that's where the roots are. And why does this help us? Because unlike the minimax polynomial, no matter what f is, we can always compute the Chebyshev interpolant. Because we have formulas for the interpolation points in terms of the roots of a Chebyshev polynomial, so we just carry out Lagrange interpolation or Newton divided differences or whatever. So at least this gives us a good approximation in the infinity norm. We know that there's another polynomial out there that can do better, but good luck finding it. So we settle for this. Or for two-norm approximation, which I'll start covering on Monday. So any questions about this? Okay. And I will what?
Excuse me, so it is not possible to find it, that polynomial.
In general, no. That's why
Just know that.
it exists and it's unique, but it's a mystery. That's why I don't like this topic, because I want an algorithm for computing it, but there isn't one. There's just a lot of theory around it. So, and I'll apologize in advance for any problems I put out there on this chapter because they suck too. So. Okay, so you guys on Monday, I'm gonna get one of you.
Okay.
So that means this is not
What?